In this video we're going to look at the influence of acquisition time per bin on the precision that can be achieved when we measure the area of a photoemission peak. The method we use for calculating the peak area is to define a background and an integration region, and then the signal that is in excess of the background signal is summed to produce the area of the peak. And in this case the region has been defined, and it is a region over a specific interval, and this defines the interval over which a background is defined, and in this case it's a linear background, and then we have to integrate signal above this background to calculate the area of the peak. And it's this calculation that we need to understand the influence of noise on how this calculation returns a value for the area. For pulse counted data, the level of noise we see in data is proportional to the square root of the counts per bin. And the way we get more counts per bin is to increase the acquisition time or increase the sensitivity of the instrument. But for a given sensitivity, we would have to change the acquisition time to achieve a better signal to noise. Hence the relationship between the uncertainty in the peak area and the length of time that we collect data. When we calculate the area of a peak, what we're doing is we're summing signal above a background. I'll illustrate this using a display option, and this involves creating sticks rather than a trace, and we can see now that the sticks above this background signal represent the area of the peak. By displaying the data as a set of sticks representing intensities that have been accumulated into individual data bins, you can see that effectively what we've done in measuring a spectrum is to distribute signal over an energy interval, and the consequence is that each individual data bin has fewer counts. And this is significant because the uncertainty with each one of these data bins is the square root of the counts per bin. So although the photoemission peak may represent a significant number of counts, the individual data bins themselves do not, and therefore by virtue of the noise being proportional to the square root of the counts per bin, the individual data bins will be far more influenced than the total of all of these data bins when integrated, and hence we use the area to represent the intensity of a photoemission peak. It might be assumed at this point in the discussion that noise has very little influence on the calculation of the area of a peak and therefore the intensity of a photoemission peak. However, this is not the case, and the problem is that data bins are involved in the calculation of the background. So the individual intensities and the noise within a data bin that's associated with the limits of a background influence the shape of the curves that then represent the background, and therefore intensities that are in excess of the background that represent the photoemission peak. So what we have to do is judge the influence of noise within each individual data bin on the calculation of this peak area because of the background calculation. The fact that the background is the significant factor in the uncertainty in a peak area is compounded by the fact that peaks sit on top of an inelastically scattered background. So the uncertainty in a peak is dependent on not just the photoemission peak itself, but it's also dependent on other photoemission peaks that occur at kinetic energies that are greater than the kinetic energy of the photoemission peak for which we're measuring the peak area. Once a spectrum has been measured, we can estimate the uncertainty in the peak area, and this is performed using an option on the regions property page. The button Calculate Error Bars will compute the uncertainty that is a result of the noise that influences the calculation of the background. I can display the information that will be generated by this Calculate Error Bars button if I enable and disable various options on the regions property page of the annotation dialog window. I've excluded the position, the full width half maximum, allowed the area to be displayed, and I've included two new options that are include area standard deviation and include area relative error. So when I press apply, a table appears, and if I then change the display so I can see the table, press the calculate error bar button, and we end up with values for the area that was previously calculated, and now because of the calculate error bar button there's a standard deviation in this area and also the relative error. So we can see that the calculation of this sodium 2s photo emission line, the area is in error by about 2% if we calculate the area based on these parameters as defined. An error of 2% is a consequence of using a linear background with an average width of 0 for these data. The linear background is constructed by drawing a straight line between two intensities, one at the start and one at the end. And when the average width is set to 0, a single data bin at either end is used to determine these two intensities. This means that the uncertainty in a single data bin is the reason the background changes and introduces the error. If we want to change the number of data bins used to tie this background to the data, we can do this using the average width. So if I set this to 3 and then calculate the error bar again, we see that the error reduces, so it's now below 1%. And the reason that it's improved is the stability of the background has improved by averaging 7 data points either end. So there's the original data point and then 3 points in and 3 points out of the integration region at each end to stabilize this linear background, and hence the uncertainty has improved in the computed area. One way of viewing the use of this average width is that the time invested in the intensity that has been used to calculate the background has now increased by a factor of 7. So had we measured the same data for a dwell time 7 times longer than the one that was actually used, we ought to have arrived at the same error that we see here. The error that we obtain for these data depends not just on the acquisition time, it also depends on how we've specified the region. So when I say that the same error, I mean had we multiplied by 7 the dwell time and set the average width to 0, then we would have obtained an error that is equivalent to the one we see here. The error that's been calculated here is based on the data that we've got. Now in general, what we would like to do is work out the dwell time that would allow us to obtain an error of less than 1%. So rather than having to wait and acquire the data, we'd like some mechanism that would let us predict the length of time that would be required for a given peak on a given background. In order to calculate the dwell time that would be required to achieve a given relative error for the area of a peak such as this one, there are options on the calculator property page that allow the simulation of data, and this allows the accumulation of signal in bins and noise that will then allow a calculation of an error, and the error can be plotted as a function of time, and so we can establish an appropriate time for a given relative error. To illustrate how these options work, it's sometimes easier to accept when you see the same type of action performed on real data. So rather than working on simulated data, the first illustration of these buttons will be based on a data set that is a set of measurements that the total acquisition time would be compatible with the measurement of a sequence of regions that were measured from a sample. This is a cerium 3+ oxide, and rather than acquiring the data into 7 VAMAS blocks, the same acquisition time has been spread over a sequence of measurements that are saved as independent VAMAS blocks. So each one of these spectra represent a poor signal to noise spectrum, but we've got many of them, and by summing them we can end up with a set of spectra with the type of signal to noise that you would expect for quantification by XPS. The option that I will illustrate using these data is on the spectrum processing calculate a property page, and it's labelled cumulative spectra. And the idea of this button is that we can sum data that are overlaid in the active tile, and the summation will be performed to create a new VAMAS file where there will be the same number of VAMAS blocks in the new file as are overlaid in the active tile, but they'll be created such that the first VAMAS block in the new file is just equal to the first VAMAS block in the old file. The second one is the sum of the first two VAMAS blocks in the old file, and the third will be the sum of the first three, and the fourth will be the sum of the first four, and so on, so that we end up with the same number of VAMAS blocks, but with each increment in VAMAS block index we will end up with increasing summation of the information that are in the original VAMAS blocks. So ultimately we will have the worst signal to noise in the first VAMAS block and the best signal to noise in the last in the new file. So I've got these data overlaid in the active tile. I need there to be one tile, so I now have the data prepared as I require. There's no scroll list here anymore. This is the only tile, so when I press cumulative spectra, and the new VAMAS file has an experimental variable that represents the acquisition time per bin in seconds, and we can see that the first VAMAS block contains 0.05 seconds per data channel worth of signal, and the second one has twice the acquisition time per bin, or the dwell time per bin. And because the counts are increasing, then as we step down this list we can see that the signal to noise, just by eye, we can see that it is improving as we go through these data, until when we reach the bottom VAMAS block we have an acquisition time that is 2.5 seconds per bin, and this is the one that would represent the sum of all of the data in the original file. The reason for processing the data in this way is that we have a progressive change in the acquisition time for these measurements. So I'm going to now create regions and then calculate the uncertainty in each one of these spectra and then plot them as a function of the acquisition time. So I'm creating a region, and in this case I'm going to make use of an offset Shirley, and let's offset the step. We're going to use an average width of 0 so that we can see a clear response to the noise as we go through these data, and then I'm going to propagate this region to all of the spectra that are selected. Now I have a region on each one of these spectra, so if I overlay these we can see how the background changes as a function of the noise within the data. So this is the origin of the uncertainty. So now let's calculate the uncertainty. The calculate error bar applies to a specific spectrum. Since we've got spectra here where we want to calculate the error bar for all of these, there's an option on the browser operations that allows the calculation of the region error bars. So now the selected VAMAS blocks will each in turn have the error calculated, and this is the equivalent of pressing the calculate error bars button for each individual spectrum. So we now go through this list, and for each spectrum there's a simulation, and this is a Monte Carlo simulation to work out how the background responds to the different levels of noise within each one of these spectra. So now every one of these regions is populated with a standard deviation in the area. We can now go to the report spec property page and make use of an option in the custom report, the button standard dev. When I press this, it populates the name formula table with the appropriate names for the area for the carbon 1s region, the standard deviation calculated for the area, and then the relative error for the carbon 1s area. So when I press area report, I get a text table which I can convert into a profile, and then I can select these individual VAMAS blocks that give me the information about how the standard deviation is changing as a function of acquisition time and the relative error. So I can see here that if I would like to have better than 2%, I would need to use an acquisition time of about 1 second. Up to this point, I've estimated the dwell time per bin on the basis of using a set of spectra that were measured. But this means the data have already been measured, and that's not the objective. The objective is to work out, before we measure the data, how long it will take to actually acquire a spectrum with the appropriate relative error for the type of quantification I'd like to perform with the data. So let's illustrate how this might be done by looking at these data here that are the sodium 2S. So I've got a count rate, I've got counts per bin, and I've got a dwell time based on this spectrum. And I've fitted the entire data with a set of synthetic components so that I've produced a residual standard deviation that is consistent with pulse counted data. And this means that I now have an envelope that I can use as part of a simulation. And this allows me to use the Simulate Spectra button and to create a set of spectra that will be equivalent to those carbon 1s spectra that I used from the measurement. And to do this, I'm going to use two fields. I've got the increment, which is set to 2, and I've got a factor that is set to 5. The increment button is the same mechanism that is used for the difference spectra and also the interpolate spectra. So when I specify 2, this means that the range 0 to 100 will be divided up into sets of 2, which means that there will be 50 VAMAS blocks created. I'm also going to use the factor 5, and this means that the counts per bin in this original spectrum and the dwell time will be divided by a factor of 5. So when the simulation occurs, the individual spectra that are created will be 50, or actually 51, VAMAS blocks that contain equivalent spectra that are simulating measurements. And the simulation is based on this envelope. So this is defining the relative intensity of the peak, and it's also defining the background. And these are both important when it comes to working out the acquisition time that's required to produce a given % relative error. So let's simulate these data now. And it tells me that there are going to be 51 simulations, and that it's going to lower the intensity and the dwell time by a factor of 5, and it's using a multiple detector system, which is what these data are. So it's producing a simulation based on a value of 0.86, which is consistent with what we see up here. It's about the same. So as far as these values are concerned, this is entirely consistent with the type of data that is displayed in this active tile. So I'm going to continue with the simulation by pressing yes. And I end up with the equivalent of the carbon 1s spectra, that I have a set of spectra, and each one has a signal to noise that is consistent with the pulse counted data, and I've got 51 of these that I can now produce cumulative spectra, just as I did with the carbon 1s. The resulting VAMAS file contains the spectra that have been accumulated in the same way as the carbon 1s were accumulated. So the first one is an example of the original signal to noise, and with each increment in this VAMAS index I have data with increasing counts per bin and increasing dwell time. So the counts per second are all the same, but we can see that the quality of the data increases as a function of this acquisition time. So the next step is to create regions and then calculate the uncertainty for each one of these spectra as a result of using a different acquisition time. So let's create a region. I've got a linear region come up. We've got an average width of 0. I'll use the average width of 0 because this is the worst case scenario. If we increase the average width, then we will alter the acquisition time that will be required to achieve a given % relative error. So this is the worst case scenario. and then I need to propagate. I'm going to propagate the region, and then before generating a profile I need to calculate the uncertainties. So if I now tick the box that says region error bars, see that I have the correct VAMAS blocks selected, and then press OK. So now it's going through doing the Monte Carlo simulation to work out the uncertainty in these areas. So once we've performed this, we can go to the Report Spec Property page, select the Standard Dev button to populate the custom report, and then press the Area Report. Creating a profile allows us to see the % relative error, and we can see now that if we wanted better than 1% in the relative error, then we would need about 5 seconds for the acquisition time per bin in order to have a relative error better than 1%. As I say, if we increase the average width, then the length of time that would be required to achieve the same relative error would shrink. So this is giving us at the moment the worst case scenario for these data.